Greetings, welcome to this new video about nodal analysis or node voltage method. Solve the problem number 11. Let's consider this network consisting of three resistors labeled R1 through R3 as well as two independent current sources IA and IB. Additionally, we can observe the presence of dependent sources, especially a current-controlled current source and a voltage-controlled current source. The question now is to find the voltage Vx across the resistor R2 and the current Ix. Let's move on to the solution. First, let's start by labeling all the nodes in the network, and I will consider this node as node 1, this node as node 2, and this node as node 3. After, we'll assign the voltage V1, V2, V3 respectively to those three nodes. Next, we need to select a reference node in the network. The reference node is typically chosen as the node with the most connections or as the ground node. Let's assign now arbitrarily the currents in each branch, and I will consider I1 is the current through the resistor R1, and this current is current I1 plus 0.8 Ix, and I2 is the current through the resistor R2, and I3 is the current through the resistor R3. Next, we will proceed to apply Kirchhoff's current law in each node. Let's start first with node 1. By applying Kirchhoff's current law at node 1, we can write I1 plus 0.8 Ix plus Ix is equal to I2. That means I1 plus 1.8 Ix is equal to I2. Let's move on to node 2. By applying Kirchhoff's current law at node 2, we can write Ix is equal to I3 plus IB. And if we replace IB with its numerical value, we obtain Ix is equal to I3 plus 5. Let's move on to node 3. By applying Kirchhoff's current law at node 3, we can write 0.25 Vx plus Ia is equal to negative I2. And we know here from our network that Vx is equal to V1 minus V3. And if we replace Vx here in this expression, we obtain 0.25 V1 minus 0.25 V3 plus 3, thus Ia is equal to negative I2. According to Ohm's law, the currents can be expressed as the voltage difference across a resistor divided by the resistance. This implies that the currents can be determined by the following equations. I1 is equal to 0 minus V1 over R1, and I2 is equal to V1 minus V3 over R2, and I3 is equal to negative V1. It actually is negative V2 over R1, and we know that V2 is equal to V1. That means I3 is equal to negative V1 over R3. Now, by substituting equation A and B in 1, we can write negative V1 over R1 plus 1.8 Ix is equal to V1 minus V3 over R2. By replacing the resistors with their numerical values, we obtain this expression. If we continue simplifying this equation, we obtain negative 7 V1 plus 5v3 plus 18ix is equal to 0. By substituting now c in 2, we can write ix is equal to negative v1 over r3 plus 5, and if we replace r3 with its numerical value, we obtain v1 plus 10ix minus 50 is equal to 0. Let's move on now. By substituting equation b in 3, we obtain 0.25 v1 minus 0.25 v3 plus 3 is equal to negative v1 plus v3 over r2. If we replace r2 with its numerical value and we continue simplifying this equation, we obtain v1 minus v3 plus 4 is equal to 0. After we finish applying the nodal analysis method, we obtain or we derive 3 equations with 3 unknowns. Let's start first by equation 6. From equation 6, we can write v3 is equal to v1 plus 4. And now by substituting a in 4, we can write negative 7v1 plus 5 times v1 plus 4 plus 18ix is equal to 0. That means negative 2v1 plus 20 plus 18ix is equal to 0. And from here, we can write v1 is equal to 10 plus 9ix. Now by substituting b in 5, we derive one equation in terms of ix. If we continue simplifying this equation, we obtain 19ix minus 40 is equal to 0. That means ix is equal to 40 over 19 is equal to 2.105 amps. And from b, we have v1 is equal to 10 plus 9ix. If we replace ix with its numerical value, we obtain v1 is equal to 28.94 volt. Let's move on now to a. From a, we have v3 is equal to v1 plus 4. If we replace v1 with its numerical value, we obtain v3 is equal to 32.94 volt. We know that Vx is equal to V1 minus V3. That means Vx is equal to 28.94 minus 32.94. We get Vx is equal to negative 4 volt. After completing the calculations, we conduct a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here is our network drawn in a SPICE simulator. We can see here this is the current controlled current source. This is the voltage controlled current source. This is the independent source IB, the independent IB, and this is the independent source IA. We have the resistor R1, R2, R3. I connect here a voltmeter in order to measure Vx, and here an ampermeter in order to measure the current Ix. Let's move on to analysis. DC analysis, calculate nodal voltage. We can see here that Vx is equal to negative 4 volt and Ix is equal to 2.11, or is just almost the same, 2.105 amps. After completing the simulation, we can clearly observe the similarity between the simulation and calculation result. This serves as a validation or verification of our work. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about nodal analysis. Take care and bye bye.